Hey guys, this is notes number 4, antiderivatives. Go ahead and write down this FLT here. It's really brief, but press play whenever you're ready. Okay, so given a derivative, okay, you're going to be able to find what we call antiderivative. Actually, it should be one word, but I don't know why they separate it. And understand what it represents. So you guys are doing two things today, okay? You're learning what an antiderivative is, but also you're trying to understand what it represents. Okay, so there's a little bit of procedural, but also a lot of conceptual too. Okay, so just keep that in mind. Okay, so here are a few problems, okay? For instance, let's say that I told you that f of x is equal to x to the third power, right? Go ahead and figure out what the derivative f prime of x would be. Okay, press play when you're ready. Okay, so here, using the power rule, you would get 3x squared. Hopefully you guys didn't forget that, okay? Okay, so keep that in mind, all right? Suppose I told you that the derivative was 2x. Okay, my question to you guys is, can you tell me what the original function was? Okay, think about this here. Take as much time as you need and then press play when you're ready. So here we're going a little bit backwards, right? We're finding the antiderivative. So here they give us the derivative, which is 2x. So that tells us that the antiderivative is x squared. Okay? Now the thing is, the original function could have been x squared or x squared plus 5, because when you take the derivative of plus 5, it goes to 0. But also, the original function could have been x squared plus 20, because the derivative of 20 just goes to 0. But the original function could have also been x squared minus pi, because the derivative of negative pi is just 0. So here you notice that the answers vary, right? How many answers do we have here? We actually have an infinite amount of answers. So when you guys are finding the antiderivative, you can't write out all of the answers. So what you do is you generalize it. So you could say that the original function is x squared plus some constant, okay? Plus some constant, so plus c. Okay, because if you think about it, if you ever take the derivative of some constant, it just goes to 0. Okay, so there's an infinite amount of antiderivatives, and you have to consider that, all right? For general antiderivatives, at least. So here's some more challenging ones. And what you're trying to do is you're trying to figure out, well, what's the rule? What's the pattern here, okay? And don't worry if you don't see it right away. Suppose I told you that the derivative came out to 4x cubed, okay? Take as long as you need to, press play when you're ready, but figure out what the original function is. The original function here is x to the 4th, because the derivative of x to the 4th is 4x cubed, right? But we want to consider the infinite amount of answers, so we put in that plus c. Okay, hopefully you got that. Now let's do one more. The derivative is, well, I'll give you a tough one. Here we go. The derivative is 8x. Press play when you're ready. This one here is a little tricky. This one is actually 4x squared plus some constant. because I know that if I have something that's linear, the original function has to be something quadratic, right? So what you guys are doing here is you're slowly picking up patterns on how this works, okay? Now, here's a gross one. Let's see if you guys can figure this one out. F prime of x equals, let's do 3x cubed. Think about what that function is, okay? And again, don't worry if you don't see it, but do attempt it and press play when you're ready. Okay, so we do notice that when the derivative is a power, the original function is going to be one more, right? So we know that this is going to be something x to the fourth, because the derivative of something to the fourth will give us something cubic, right? Okay, this is actually 3/4 x to the fourth plus c. And you can just stare at that for a while. If you take the derivative of 3/4 x to the fourth plus c, you'll get 3x cubed. Okay, so how do we come up with a pattern so that we can kind of just figure this one out here, okay? Think about what the rule is for derivatives, right? If I gave you guys some power x to the n, the derivative, okay, some of you guys might say, well, you bring down the power. Now, for instance, actually, I'll use a value here so that it makes more sense for you guys. Let's say we had x to the fifth, right? Our answer here would be what? We would have a 5x to the fourth for a derivative, right? Now, really what's happening here is, I mean, some of you guys might say that you bring down the 5, but physically what's happening, right? Physically what's happening is you're taking the power and you're multiplying the power. Okay? So when you bring down the 5, you're really multiplying it by that number, okay? And what happens to the exponent? The power is 1 less, right? So the exponent of 5 became an exponent of 4. So if you think about an antiderivative, right, it's pretty much going in the reverse process. So just think about this here. Instead of making the power 1 less, the antiderivative does what? Right? And instead of multiplying by the power, the antiderivative does what? So think about that and press play when you're ready. Instead of making the power 1 less with the antiderivative, okay, we're just going to make the power go up 1. The power is 1 more. Because that's the definition of an anti, right? It's the opposite. And instead of multiplying by the power, we're just going to divide by the power. Okay? So, here's how this works. For instance, if you guys had the derivative is, let's say, x to the 8th, the original function, okay, so we're finding the antiderivative, the power is going to be 1 more, 8 plus the 1, and then we're going to divide by that new power, which is the 8 plus the 1. Okay? And we don't forget our plus c, right? So this is really just x to the 9th over 9 plus c. Okay? So the rule is this. If your derivative is some x to the n power, your original function is going to be x to the n plus 1 divided by n plus 1. Obviously with a plus c. And this is your rule. Okay? You can find this on your calculist If you remember that sheet there, that PDF that I sent you guys, make sure that you guys have that, okay? Good. So, for instance, if I told you that the derivative is x to the 12th power, go ahead and figure out what your original function is. Press play when you're ready. So this is going to be x to the 13 over 13 plus c. Okay? When you take the derivative of this function, you're going to get x to the 12th again. Okay? So hence derivative and antiderivative, they work in opposite directions, okay? Now what this all means, I'm going to explain to you guys at the very end, okay? So here's the next one. Let's say that the derivative was the square root of x. Okay? I want you guys, I know I'm not labeling these examples yet, but just write it down. Okay? Think about what the original function is here. Press play when you're ready. Okay, so what you're trying to do is, with the antiderivative, you're trying to use that power rule, okay? Now, similar to derivatives, when they don't look exactly the way you want it to, it causes you to rewrite this, okay? So the square root of x, if you guys remember, is the same thing as x to the 1/2 power. So if I use that power rule for antiderivatives, that's just going to be x to the 1/2 plus a 1 over 1/2 plus a 1 plus c, right? Okay. Now, I know I'm writing out all the work, and later on, you guys are going to be able to cut your corners, which is absolutely fine. So this is going to come out to x to the 1/2 plus 1 is just 3/2. Think about how I got that. And then I'm going to divide it by that same power, 3/2. Okay, even more so, when you divide by a fraction, you're really multiplying by the reciprocal. So this is really 2/3 x to the 3/2 plus c. Okay, so the idea here is, if it doesn't look the way you want it to, fix it, right? Here's another one. Let's say the derivative is 1 over x to the 5th power. Think about how you would do that one there, okay? Press play when you're ready. Okay, so here, because it's not perfectly set up like a power, what we want to do is rewrite this. If you guys remember, with fractions, you can rewrite it so that there's a negative exponent. So 1 over x to the 5th is really x to the negative 5th. And now that it's perfectly set up, I can use that power rule for antiderivatives, which is just x to the, we're going to add 1 to our power. So that'll be negative 4. Be careful with that. Don't put negative 6. We're adding 1 to our power, and we're dividing it by the same power, plus the c. Okay, and if you want to rewrite this, this would just be 1 over negative 4x to the 4th plus the c. And that's it. Okay? Let's keep going. So, a little refresher. Back when you guys had the function, not the derivative, okay? Back when you guys had the function that was 8x cubed, think about how you found the derivative, right? Now, obviously, the derivative here is 24x squared. You guys have done that enough. But really what's happening is, when you have a constant, 8, you kind of ignore it. You just put it to the side, and then you take care of x to the cubed, which is 3x squared, and then you multiply the 8 and the 3 to get you the 24. But we do that at lightning speed, right? We might even skip that orange step. But the whole idea with this constant multiple right here is that you ignore it and then you bring it back. The same thing happens when you're finding antiderivatives. So let me give you an example here. Let me get some space. Okay, so let's say I told you that the derivative is 4x squared, okay? Finding the antiderivative is the same thing. So that 4 is a constant multiple. We call it a coefficient. So what you do is you ignore that 4. You just bring it down, okay? Then what you do is you find the antiderivative of x squared, which is just x to the third over 3 plus the c. Okay, and then you could smush it together to make it look pretty. This will be 4/3 x cubed plus the c. So when you have constant multiples, you just push it to the side and then you bring it back. All right, let's try one more. Let's do the derivative is 15x to the 4th power. Okay, press play whenever you're ready. So the original function would be 15. Okay, we just move the constant. And then x to the 4th is just going to be x to the 5th divided by the same power plus the c. Now this one here, we're actually able to reduce the 15 and the 5, so that becomes a 3x to the 5th plus c. That is our original function. And it kind of makes sense because if you take the derivative of 3x to the 5th, you're going to get 15x to the 4th. Okay? So you guys are just working backwards. So you're learning how antiderivatives work. Okay? So, here are some weird ones. Okay? Some weird ones that you guys should know. Let me make more space here. I'll just add a new page. Okay, so what if you guys had the derivative is 4x to the 5th plus 3x squared minus 4x to the 3rd power, okay? So similar to derivatives, with the sum and difference rule, you're just going to take the derivative of each, right? The derivative of a sum is the sum of each derivative. So antiderivatives work the same way. You just go ahead and you take care of the antiderivative of each, okay? If it's separated by a plus or a minus sign. So press play whenever you're ready here, but try it out. This is going to be 4 times x to the 6 over 6 plus 3 times x to the 3rd over 3 minus 4 times x to the 4th over 4, and don't forget your plus c. Okay? So a few things to address. You could smush this together and clean it up. 4 and the 6 here will reduce to 2/3 x to the 6 plus x cubed. The 3's will reduce out. The 4's will also reduce out, so minus x to the 4th plus the c. Now, some of you may be asking, this plus c, do I write plus a constant, plus a constant, plus a constant? Do I have to write it 3 times? Okay? And here's the idea. Let's say you wrote it 3 times, right? Well, the 3 green c's, 3 green c's, c plus c plus c is just 3c, right? But if c is a constant, some number, and you multiply by 3, you're just going to get some other constant. So the moral of this story is you don't have to write it every time. You just got to write it once at the very end. Okay? And then this is our original function. Okay? Here's some weird ones. Let's say I told you that the derivative was cosine. Okay, what is the original function? Press play when you're ready. Okay, so when you're not dealing with power functions, you cannot use the power rule. Okay, you can't say that this is cosine x squared over 2. This is a trig function. So you got to think, the derivative of what function gave me cosine? So in this case, it's sine. So you got to think about all of your other non-polynomial functions, okay? Now here's a weird one that you want to pay attention to. Suppose that you had some function and the derivative came out to sine x. Without looking at your calculus, think about what the original function is. The original function here is negative cosine because the derivative, the derivative of cosine is negative sine x with an extra negative on the outside, which would turn it into positive sine x. Okay? Make sure you guys know how to go forwards and backwards with sine and cosine. That's probably the #1 mistake people make. Okay? And again, on your calculus, you have all the other ones, right? So don't think of it as an extra set of formulas that you have to remember. As long as you know your derivatives, you should be good. For instance, if the derivative came out to secant squared x, you guys should know what the original function was. Okay? That's just tangent x, right? And I'm not going to go through all of them, but you should know the antiderivative. So here's the one that tends to throw people off the most. Okay, go ahead and figure out what the original function is here. Press play whenever you're ready. So I'll show you the wrong answer first, okay? What most people do here is they'll say, wait, 1 over x, that's the same thing as x to the -1. Okay, so that looks like a power, so that's going to be x to the 0 over 0. But wait, that's weird because we can't divide by 0. Okay, so I kind of lied to you guys. Back here with this power rule, there's a stipulation, okay? They state that n cannot be -1. Okay, so knowing that if n is -1 here, you would have x to the -1, which is really 1 over x. So this power rule does not apply to 1 over x, and there's a reason why. For one, you can't divide by 0, but more importantly, there is a function where if you take its derivative, it comes out to 1 over x. Okay, feel free to look back into your first semester here, but try to find it on your own before I tell you. Press play when you're ready. So there was a function where the derivative of it gave me 1 over x. Okay, that was the natural log. Okay, the derivative of natural log is 1 over x, which is the reason why you can't use the power rule. Okay, so again, this is probably the #1 mistake people make, so make sure that you understand the antiderivative of 1 over x is the natural log of x, okay? So you have this long list, and I didn't go over all of it, but this is basically what you guys have, okay? So some things that I didn't cover, okay? For instance, it's kind of intuitive. We know that the derivative of some constant is 0. So the integral or the antiderivative of 0 should be some constant. Kind of makes sense, right? So let me write that out. So for example, if the derivative was 5, if the derivative was 0, then the original function was just some constant like 6. Okay, but in this case, it would just be some constant. Okay, and I'll write this next one out because it tends to throw people off. Let's say that the derivative came out to 4. Okay, what is the original function? Okay, so 2 ways that you can kind of look at this so that it makes logical sense. Remember that derivative means slope, okay? So here the derivative is at a constant 4, meaning that the derivative is constantly 4. The only time a function has a slope that's constant is when you're dealing with a linear function, because a line has the same slope every single time. Okay? Now, procedurally, you guys can think of this as 4x to the 0. So that's really just 4x to the 1 over 1 plus c, which is just 4x. But whenever your derivative is a constant, your original function should be linear. Make sure that you guys know that because it does pop up very often, okay? And it's right here. Integral, or the antiderivative of a constant, is just some constant x, okay? Here is your constant multiple rule, where you ignore the constant and you bring it back later. Here is when you're taking the integral of a sum or a difference, you're just taking the antiderivative of each, okay? And here's your power rule, where n cannot be -1, because if n is -1, it's right down here, you get natural log. You got a bunch of, trig functions that you guys want to go back and check. Okay. Here's another one. The derivative of e to the x is e to the x. So the integral of e to the x, or the antiderivative of e to the x, is just e to the x. That's easy to remember. Now these two right here, I'm just going to hold off until later, only because it doesn't pop up very often on the AP exam, but I will cover it if we do run into it, okay? Okay, so here we go. Rapid fire, okay? Try these 4 real quick. So, this is the integral, and I use it in the same fashion as the antiderivative. So I want you guys to understand right now that antiderivative, I can't spell, antiderivative, and integral, or integration, are the same thing for now, okay? So here, I'll do the first one with you guys. The integral of 1 over x cubed dx is the same thing as the integral of x to the -3. I'm rewriting it. And then the integral of that is just x to the -2 over -2. We increase the power by 1, and we divide it by the same new power, plus a c. This comes out to 1 over -2x squared plus c. Okay? Actually, I think we did part B already earlier. Go ahead and try part C and D, and press play when you're ready. Part C, notice how there is a coefficient. So what you guys could do, this step is not necessary, but it may be easier on the eyes. That 2 is a coefficient, so that 2 could actually go out of the integral. And then you could just focus on the integral of sine x, or the antiderivative of sine x. And that's just going to be negative cosine. Okay, so if you clean that up, that comes out to -2 cosine x plus c. Okay, here's the last one. 3 is a coefficient, so you could actually take that out. Now what's left is going to be an invisible 1 there, right? Okay. Now, the integral of 1 over x, remember, you cannot use the power rule there. The integral of 1 over x, or the antiderivative of 1 over x, is just the natural log of x plus the c. Okay, so that's just 3 natural log of x plus c. It should actually be the absolute value, but we'll talk about that later. Okay, so you guys have practice on that, all right? Here's another one. I know I didn't list any examples here, but you have enough practice, okay? Press play whenever you're done with this, or if you're stuck. Okay, so this is the same thing as 10 integral of x to the 4th dx minus 2 integral of secant squared x dx. So notice how every integral has a with respect to some variable, okay? So they always come in pairs there, all right? And notice how the coefficients are always outside of the integral to make it easier, okay, visibly. So here we have 10 times x to the 5th over 5 minus 2. And the integral or the antiderivative of secant squared x is just tangent x. And don't forget your plus c. If we clean this up, this becomes 2x to the 5th minus 2 tangent x plus c. This is the original function here, okay? Okay, so you guys have a good idea of how to find the antiderivative, but what the heck? Like where do antiderivatives come from, right? We were talking about approximating area under a curve, and then all of a sudden we're doing antiderivatives. Like, where's the flow in that? So here's something I want you guys to think about. This next part here, you just need to watch, okay? You could write it down if you'd like, but I would rather you guys just watch. So here we have a picture, okay? This, don't worry about all of these calculations on the left there, okay? That was really for me, not for you. So I made this illustration for you guys. Suppose that this red curve is just some function. We don't necessarily know what this function is. And suppose I wanted to find the area under the red curve from the green line to the purple line. Okay? So, for instance, what we're doing here is we're trying to find, is it this? We're trying to find that purple area. How do I do that, right? So, I'm going to do a few things, and I'll annotate for you guys so that you can see it afterwards. So, here's your first area, okay? From the y-axis all the way up to the green line, okay? This is the area under the curve, the green area, okay? Now, this right here is the area under the curve from the y-axis all the way to that purple line, okay? So, to think about that purple, the way I would get that purple shaded region is all I would have to do is I would have to just take my red area and subtract out that greenish part so that I can get my purple. Okay? Make sure that you guys understand that there, okay? So in order to get the area of that purple part, I would just have to take all the red and subtract out that green part. And then I would get the purple. Okay, so what does this all mean? So here we go. Hopefully I can, show this to you guys. Let's, Pokemon, yay. Okay, so here was our picture, all right? I'm going to annotate this for you guys. So let's suppose that we're just being generic about this here, okay? We're just going to call this, I shouldn't put a point there. Let's just call that x. So here at that point, that should be x comma whatever the function is. Okay? Now, let's say I stop at some other point. Sorry, I stop at some other value. Let's call this x, stop it, you, okay, x plus however much I moved over, okay? And that point hits the curve right there. That is x plus h, comma, whatever f of x plus h is, okay? So there's a lot going on here. So let's start off with this. The green area that we had, okay? Let's say we found out what that green area was, okay? And I'm just going to call it capital F of x. Okay, meaning the area here. So I'll just call it capital F of x, all right? Now, everything in red, I'm going to call capital F of x plus h because I went all the way up to x plus h there. And this will be the red area. Okay? And then there's that purple area, which is what we're wondering about. I know there's a lot of highlight here, so I'll try to not scribble over everything. So that purple area is from right in between the the vertical bars there, okay? Okay, so I'll write this out so that you guys understand what we're doing. In order to get the purple area, okay, I would have to take the red area and I would have to take out or subtract the green area. Okay, hopefully you guys are with me still, all right? In order to get the purple shaded region, I have to take the red, which is the whole thing, and cut out the green part. So in this case, the purple area is really just the area of the red, which is capital F of x plus h, minus the green area, which is capital F of x. All right? Okay, so here's what we're going to do. Just taking a look at the purple area, and we'll go back to this screen so that you guys can see it. Just taking a look at the purple area. You guys have learned how to approximate this area, okay? And just for the sake of simplicity, we're going to use rectangles, okay? So here, I am going to purposely use a left Riemann sum, okay? I'm going to draw one giant rectangle where the left corner touches the curve. So it would look a little bit like this, and I'll use the dotted lines for you. So if you take a look there, if I were to approximate that purple area, I would use the left Riemann sum there, and that would be that shaded region right there, okay? So definitely this is an under approximation because I didn't cover all of the purple, okay? So think about this here now. Let me take a picture of this. Let's say that I wanted to, I think it's this one. Yeah, okay. Let's say that I wanted to approximate this green rectangle, okay? So I want to remind you guys that this right here was x and this right here was x plus h. Okay, so this was also, let me use the same color so that we're not confused. This right here was x comma f of x, and that up there was x plus h comma f of x plus h. Okay? Okay, to find the area of a rectangle, it's going to be the base times the height, right? So take a look here. How would you find the length of this? Press play when you're ready. That would just be the end minus the beginning. So x plus h minus x, that width would be h, okay? Now, how do you find the height of this rectangle here? Press play when you're ready. Since this is a left Riemann sum, the height is determined by the left corner of the rectangle. So in this case, this is the height. But how do we determine that height? That's the y value. Okay, almost done, you guys. So the area of this green rectangle is h times f of x. I'm going to put that right here. So h times f of x, okay? And this is just an approximation to what the purple area really is, okay? So here's what I'm going to do. I'm going to go ahead and do a little bit of algebra here. I'm going to go ahead and divide by h on both sides, okay? This will give me f of x is approximately capital F of x plus h minus capital F of x all over h. Okay? So this is where it counts, all right? If you take a look at my approximation and you take a look at the whole area, they are not the same, okay? But what happens if I take the h, meaning how far these two bars are, if I slowly scoot that h closer and closer, will the green area be the same as the purple area? Okay, so as of now, it's definitely not the same area, but theoretically, and I'm going to speed this up because I'm running out of time, theoretically, as I get arbitrarily close to zero, meaning as these two vertical bars get arbitrarily close to zero, that purple area should be the same as the green area. Kind of a weird concept, okay? Theoretically, if I get super close, arbitrarily close to zero for h, that green area will be the same as the purple area. The same, okay? So keep that in mind. So here's what happens. If I get arbitrarily close to zero, that is what we call a limit. If I take the limit as h goes to zero of capital F of x plus h minus f of x all over h, this now becomes equal to f of x. Okay? The two areas are now equal in theory, okay? I got to squeeze in one more page here. Okay, so think about where you guys have seen this notation from. Okay? That looks very familiar. That is, in other words, the derivative of whatever the function is. So in this case, this is capital F prime of x. Okay? And I'll bring everything else down. And again, you don't have to write this down unless you want to. Now, think about what this really means, okay? Capital F meant what, right? Capital F meant area, right? So, in other words, this is the derivative of the area, okay? And we'll just call this f of x, all right? So, what does that mean, right? So if I were to, let's say I want to focus on what area really means, right? To get rid of the derivative, I would just take the antiderivative, right? And what I do to one side, I do it to the other. So really, the area is the antiderivative of the function. Here's why this is so powerful, okay? Now we've made a clear connection. You guys know three things now. You guys know that when we integrate or we take the integral, that's really just the antiderivative. Okay? But what the heck is the antiderivative? The antiderivative is really finding the area under a curve. So this is the new concept with calculus. We've been approximating area under a curve, but now we can actually find out what the exact area under a curve is because we know that by integrating or by finding the antiderivative, that is exactly the area under a curve. Let that marinate for a little bit, okay? So big takeaway, kind of like when you guys learn derivatives, Derivative was an instantaneous rate of change or the slope of a tangent line, right? Now when you guys integrate, you have to understand that integral means the antiderivative, but more importantly, it's the area under a curve. You're accumulating all this space from one moment to another, okay? That's it for today, okay? You're going to practice on antiderivatives and how does it really connect with everything else afterwards, all right?